Hey, what's up, guys? Today I want to show you guys a really cool proof. And so we're going to start by considering 2 points on the unit circle, A and B, I'll call them. So I want to consider A to be at a position that makes an angle alpha, and I want to have B at a position that makes an angle beta. So if we remember, a point on the unit circle will have coordinates of cosine the angle that it makes, um, comma sine the angle that it makes. So that's why you see here that A is at this point and B is at this point. And I just want to remind you guys about the distance formula. It's not anything mysterious. It shouldn't be something that you have to look up. It makes perfect sense when you think about it because it just considers a right triangle that you would make between these 2 points. Considers what the difference in height is, in other words, the height of the triangle, and the difference in width is, in other words, width of the triangle, and then calculates the hypotenuse, the length of the hypotenuse, which will be the distance in between A and B. So here I am calculating the distance between points A and point B. Okay, so let's just keep this expression in our back pocket for now. Now I want to consider rotating A and B so that B sits here on the axis. And so A will slide down by an angle B. And so the new point A will sit at this point because it started at A and then it slid down B. And B will be at the point 0, 1. So if we consider here's our old A and our old B, and then we slide it down by angle B, we take both of these points and we slide them down by angle B. Now the new B is here on the axis and the new A is here. And I'm going to call the new A prime and the new B prime. That is a prime convention that is used pretty frequently, actually. So what we have here is we're looking at the position of point A. It is the cosine of alpha minus beta. That's its x coordinate because it started at cosine of alpha and then the angle got shifted by beta, so its new location looks like this. And we know that B prime is at 1, 0 because it's still in the unit circle. So this is me here writing down the distance formula for the distance between A prime and B prime. And so the way I did that was I just used this new location, this new cosine and this new sine. You'll see them here. Okay? And now, I mean, if it wasn't obvious from before, I'm going to bring in my tools. My tools are the fact that A and B, the length there is the same as this length, A prime and B prime, because the points relative to each other haven't changed because I've changed both of them the same. So length AB is equal to length A prime B prime because they are the same. And so what I'm going to do is I'm going to set the equations equal to each other, the expressions of their distance, okay? And so it's easy enough. I've got them here at the top. You don't want to say, I mean, I put here that I square both sides and expand, but it is not truly that you are squaring both sides per se, because we're not going to make an absolute value statement out of this. We're not going to concern ourselves with plus or minus because if we notice the arguments of the radicals are always positive numbers because they're squared. So I'm basically going to say that if the square root of this equals the square root of this, and this is always positive and this is always positive, then I can be sure that I can just take these radicals off and I can just compare them with each other without the radicals. So this is me expanding here just the left-hand side. This isn't both expressions. This is the left-hand side because I've expanded it. I've FOILed this to get this, and I FOILed the second term to get these sine terms. Okay, So now I'm going to show you, here's the top equation, here's the left-hand side. Now here's me removing the radical and expanding the bottom. Notice that sine alpha minus beta has a minus 0 here. So when I square it, it's just going to give me sine alpha minus beta. Okay? So while this top term, this turned into 3 terms, this turned into 3 terms, so you had 6 terms. This turned into 3 terms, and this guy over here only turned into 1 term. So that's why we have 4 terms down here at the bottom, much smaller right-hand side. So this is that same statement again, and now what I'm showing you here with colors is that with the blue here, I want to show that cosine squared of alpha and sine squared of alpha are both in this expression combined through addition. And cosine squared of beta and sine squared of beta are both in this expression combined through addition. So we see that we can say that the cosine squared alpha plus sine squared alpha is 1, equal to 1, and cosine squared beta and sine squared beta are going to be equal to 1. Likewise, on the right-hand side, we have a cosine squared of alpha minus beta and the sine squared of alpha minus beta. So they're going to combine to make 1. And so here's a visualization of that. We got our blue one, we got our red one. These two terms are not going to change for now. We have on the right-hand side, we have our blue one, and we have our one that we brought over for that was always there. And we have our minus 2 cosine alpha minus beta. This was the cross term, remember, from cosine alpha minus beta minus 1 quantity squared. This was the cross term. That's why that's there. So obviously I've got 2 on both sides here. Well, this is me just putting it on one line. Okay, we've got 2. I combine the 2 ones. Minus, these terms are both minus. And on the other side we have 2 minus, and then this term is also 2, negative 2 of that term. So here I am showing those 2 steps again, and then canceling the 2's out and dividing both sides by negative 2. So when I do that, this becomes a positive sign, right? Because negative 2, this stuff, divided by negative 2 turns this into positive sine alpha times sine beta. So this equation turns into this equation, and this is our identity. This is the important thing. This is going to do a lot of work for us. The equation, as it is boiled down, I have here, just in case my handwriting wasn't agreeing with you. So, but it is usually written, I have here shown that it is usually written in this form. Because normally you're looking at this and you want to be able to give this. It is normally you are not going from this to this. You're normally going from the smaller to the larger. You're normally expanding so that you can have trigonomic functions that have either alpha or beta and not some or difference. So normally you'll find it in this form, but this is it. And that's great. Thanks for watching, guys. And I hope that you will watch the parts again that you find useful, and you will come to class with a deeper understanding of what's going on here. And I would like you guys to push your thinking on this, and I would like you guys to consider this equation. Now consider this equation under these cases. Okay, consider what the right hand side would look like if instead I wrote alpha plus beta. Okay, I'll give you a hint. That has to do with the even or oddness of the trig function. So I want you to consider cosine alpha plus beta. What would the right hand side look like? I want you to consider what will happen if beta is equal to negative alpha. I want you to consider what will happen if alpha is equal to beta. What will the right-hand side look like? And then I want you to consider what alpha equals pi over 2 will look like. And so if you guys will do this on a separate sheet of paper or whatever, bring this in with you. I would like to talk about these things. So I have four cases under which I would like you to consider this equation, this function. So this is our cosine of angle difference formula, this guy here at the top. And you'll be seeing a lot of it, I'm sure. Thanks for watching again, guys, and I'll see you soon.